Large-scale AI models depend on dense routing matrices to move data between layers. Every operation requires a calculation of thousands of probabilities to determine a data path, consuming massive amounts of compute for a single token. In sparse mixture of experts routing, this produces a tangled web of arbitrary probabilistic connections, where paths are guessed and recalculated on the fly. These calculations force the system to waste computational resources on pathfinding alone. Under pressure, these probabilistic models often degenerate, leading to inefficient routing and stalled processing. A geometric alternative bypasses this guesswork entirely. By replacing learned probability with exact discrete mathematical geometry, network routing moves from a stochastic estimate to a deterministic law. Shifting from probabilistic guesswork to geometric determinism targets the scaling bottleneck at the hardware level, aiming to decouple model capacity from raw compute intensity. The blueprint for this architecture comes from number theory. The prime number sieve, traditionally a tool for identifying irreducibles, functions here as a mechanism for navigating vast computational search spaces. This application relies on looking at primes through recent breakthroughs in analytic number theory, specifically regarding prime gaps and divisor expansions. Terence Tao's research identifies a structured, discoverable geometry within the prime number sequence, identifying patterns that remain consistent across the number line. James Maynard expanded this theoretical bedrock by mapping the exact geometric constraints and divisor sums that govern how primes are distributed. By mapping network routing constraints to the recursive, admissible pathways described in these theories, researchers developed a new computational model, the prime transport router. This converts abstract number theory into a physical, highly efficient computational primitive for artificial intelligence. The core conceptual bridge is translation. In this architecture, the prime sieve operates as a system of exact, recursive admissibility masks. The mapping is direct. Mathematical prime candidates become the network's candidate next states. Mathematical wheel filters, used to narrow candidates, become the network's routing constraints. Finally, the surviving tuples within the sieve function as allowable continuations, defining valid paths for data flow. Stacking these local admissibility masks allows the system to natively filter out invalid paths. The network doesn't have to calculate every probability. It identifies correct continuations by the geometry of the search space. This allows a massive search space to naturally collapse into validated structural pathways without the need for brute force search. These partitions occur within a discrete mathematical geometry, an SO8 hypersphere routing chart. Operating on a normalized hypersphere allows the system to compress decision effort. The router relies on the angular properties of the geometry rather than complex learned policies. This chart shows the routing compression ratio on the y-axis against routing resolution on the x-axis. As resolution increases, the compression scales monotonically from 1.17 to 1.97. These results are remarkably stable. The variance across initialization seeds is microscopic, showing a standard deviation under 0.02. In standard AI models, forcing finer routing resolution usually introduces noise and collisions. In geometric routing, the opposite happens. Finer resolution amplifies the routing advantage. Because the mechanism is inherently angular and self-organizing, increased capacity leads to cleaner data separation, validating the geometric hypothesis. In this system, a low-scale route acts as a coarse semantic bucket. As data moves deeper into the network, that bucket is recursively refined by new prime layers. Each added prime layer contributes a new refinement angle. This compresses the state of the route, rather than adding computational weight. This mathematical formula is R-min, a vector composed of a base angle, a phase, a radial depth, and a next return gap. This state allows the router to write observations into reusable memory cells, only promoting queries to a richer memory branch when a path remains unresolved. Researchers evaluated this memory layer using a bounded, stateful task loop to measure its ability to reuse data across changing tasks. The results showed an evaluation read-hit fraction of 1.0, with an exact branch retrieval rate of 0.719. The system recorded exactly 0.0 instability throughout the loop, proving it functions as a highly stable, structured read-write memory machine. To make the controller efficient, the architecture needs an explicit attractor identity, a way to recognize where different data paths converge. This convergence is generated naturally by the discrete geometry, following a strict prime-divisor hierarchy. This chart visualizes the network as a navigable divisibility graph, connected by shared mathematical factors. Highly divisible numbers serve as major routing hubs, where data streams intersect. Prime numbers occupy the extreme ends of pathways. Being irreducible, they function as stable atomic anchors. Data pulses navigate these structural junctions, filtering through the divisor hierarchy to reach their atomic endpoints without processing collisions. This divisibility graph provides the convergence identity the controller needs to route data cheaply and deterministically. The physical implementation of this model was tested via a large-scale reintegration experiment. Early iterations hit a performance ceiling. Researchers found that additive signal injection at every step was poisoning the substrate and masking the geometric signal. The fix was to restrict additive token injection exclusively to step 0, the initial encoding step. Injecting only at step 0 preserves expressiveness while allowing the signal to travel as an undistorted wave across the remaining time steps. Clearing this signal ceiling proves that discrete geometric routing can carry clean, functional information across a live neural network. The prime transport router has moved from a number theory analogy to a fully realized computational primitive. It completely replaces the old, chaotic, dense routing matrices with perfectly ordered, deterministic, and highly efficient geometric data flows. By utilizing delayed refinement and structured prime divisor reuse, the system eliminates the need for probabilistic guesswork. This transition offers a potential 10x to 100x reduction in raw compute requirements for large-scale models. Geometry and analytic number theory provide a path to these massive compute reductions, bypassing the scaling limits of current dense architectures.